All right, this is going to be 2 pages, the first 2 pages of our notes tonight, and it's on thermochemistry, a major unit in AP chemistry. Face it, everybody likes fireworks, a warm fire, food cooked on the grill, and all of that requires the use of energy. So chemical reactions that are accompanied by energy changes come in various forms. Some examples might be, as I just mentioned, burning methane in the presence of oxygen gas. So when we burn methane in oxygen gas, we get energy from that to cook steak on a grill. I just had that for dinner, so thankful for that ability. And then electrical energy is often needed to decompose water. So there's a lot of ways that we can talk about energy in chemistry. What is thermochemistry? Specifically, the word thermo applies to heat energy, and it's the study of heat flow in a chemical and physical change. So let's write that down. What is heat? I'll give you a second here. What is heat? Heat is a form of energy. So there's electrical energy, there's potential energy, kinetic energy. Heat is one of those forms of energy. It is the energy that is involved when there is a transfer of energy between two objects of different temperature. So heat is described as the transfer of energy between two objects of different temperature. So when you put your hand on something that feels cold, it feels cold because you are giving your energy to that object. Heat is symbolized with the letter Q, so keep that in mind. Let's underline that or circle that. That's an important thing, symbol Q. This is important to note that the direction of heat flow is always from a sample of high temperature into one at a lower temperature. So I like to think of that as, how can you give away your energy if you don't have any? So the thing that has the energy gives it away to the thing that doesn't or has a lower amount of energy. Heat and temperature. Okay, this is a discussion about an intensive versus an extensive property. We've talked a lot about temperature recently because we've been using our gas laws, and temperature is a measure of average kinetic energy. You just got tested on that, so come on, guys. Temperature measures the average kinetic energy of the particles in a sample. It is an intensive property. Notice what I wrote down here. Water at 1 atmosphere will boil at 100 degrees Celsius no matter the amount. So if I have a cup of water or if I have a gallon of water, it's going to boil at 100 degrees Celsius. That means that temperature is an intensive property. So it doesn't matter how much you have, it's going to be the same temperature. I can have a room at 25 degrees Celsius. I can have a small flask at 25 degrees Celsius. Heat is different. Heat's a form of energy that is an extensive property. Now what that means is that it depends on how much matter you have. So the more heat that you want, the more matter you're going to need. I have more wood, more heat. So if you're sitting by a campfire with your friends and the fire starts to dwindle down, everybody will say, throw another log on the fire. The study of heat flow of a chemical or physical process can be divided into 2 areas of study. And right here, this can kind of get a little bit confusing for students, but it's important to realize that in the chemistry world, we define everything by the surroundings. So let's put a star by that. We are going to define everything from the surroundings. Okay, let's fill in what a system is. The system is the actual chemical or physical process that is under observation. So the system is the actual chemical or physical process that is under observation. So for example, if I want to know how much energy does it take to melt ice, then the system is the ice. Where is that energy going to come from? Well, how am I going to melt ice? Well, I need energy from someplace, and that is the surroundings. So the surroundings would be any material that is touching the system. If I'm going to melt the ice on my hand, then my hand is the surrounding, and the air as well. If it's going to be in a beaker, the beaker becomes the surrounding, the air as well. So surrounding is anything touching the system. If you combine the system and the surroundings, you get something called a universe. And in chemistry, we study micro-universe. I know you're thinking large-scale universe, you're thinking the planets, the sun, the moon, all that stuff. But I'm thinking just how about a styrofoam cup with a lid? And inside of that styrofoam cup, inside that styrofoam cup, there's a piece of ice, and we add water to it, and we measure the temperature change as the water melts. Well, that would be a system, the ice melting, the surroundings, the water in the cup, and that together, if the lid's on it, it's going to make a universe. Now, styrofoam works really well for a universe because it's an insulator. So any heat that is taking place in the transfer isn't going to be lost outside of the cup. The styrofoam is going to keep it in there. According to the law of conservation of matter, energy is neither created nor destroyed during a chemical or physical change. So any heat that flows out of the system has to be going into the surroundings. This right here is a very important relationship. This is something that, when we look at the problems, you guys are going to say, I don't know how to solve this problem. And I'm going to look at you and say, well, what do you know is true about the system and the surroundings? So if they're asking you something about the surroundings and you know the energy of the system, you know some information about the surroundings because it's the opposite of the system. Look at the notation. Q system, the energy or the heat. Remember up here, look at where we circled it. Heat is symbol Q. The heat that is lost by the system would be gained, and that's why that negative sign there, would be gained by the surroundings or vice versa. Whatever this gains, this is going to lose. All right, so make sure you get that page. That's page 1. Moving to page 2, we're going to talk about something that is a review from last year. So some of this stuff is going to sound very familiar. When we assign a positive value to Q, so let's say we calculate heat, and we end up finding out that the heat is positive. What that means is that it's called an endothermic reaction. And hopefully you remember this from last year. An endothermic reaction is when the system absorbs energy from the surroundings. The heat flows into the system. I want you to look down at the bottom of the page at this diagram that I labeled as endothermic. Here are the surroundings, and here is the system. And look at how the energy is going into the system. Look at how the arrow is pointed upwards. That means that the potential energy of the system is going up. The potential energy of the system is going up. How could that happen? It's happening because it's gathering energy from the surroundings to cause the chemical change. One thing that I want you to note up here, look at how we assign everything from the system's perspective. So what does it say? Endothermic. System absorbs energy from the surroundings. Because it's gaining energy, it will be positive. Heat is flowing into the system, so it's positive. This is a curious venture for students, something that students don't get very often. Let's draw a styrofoam cup. Let's see if I can zoom in here. Oh, sorry. Ooh. Okay, styrofoam cup, let's put some water in it and a chunk of ice. So this is my ice. Okay. Students do not often understand. That's a thermometer, people. This is my fancy thermometer. Okay. If I asked you to predict, what do you think will happen to that thermometer as the ice melts? This should be a pretty obvious exploration, and yet it causes problems for a lot of students. That thermometer is going to go down in temperature. The thermometer will go down. So the thermometer, let's write that in, will go down. Think about why it's going to go down. Where is the thermometer? It's in the surrounding. It's in the water surrounding the ice. And that ice can't melt without the energy of the water. So as the water loses energy, the temperature of the water is going to go down and your thermometer will go down. But what that means is that the system is absorbing energy from the surroundings. The opposite is true. Hopefully you remember from last year when Q is negative, it's an exothermic reaction. The system releases. I like to think of it as exiting. The system is losing energy. Who is it losing it to? Take a look at the diagram here. System is losing energy to whom? It's going into the surroundings. And that's an exothermic reaction. Exothermic reactions, the system releases energy to the surroundings. Heat flows out of the system. It exits. So EX, EX. Here in endo, you can think endo enter, exo exit. Okay, and it's all from the perspective of the system. Aren't we having fun? We're at 10 minutes and 31 seconds. All right, so example number 1 here. I want you to look at, this is an exothermic process. There was no Q value given to you, but you can tell this is exothermic. Why? Because there's the reactants, here's the arrow, and here are the products, and look at where heat is listed. Anytime heat is listed as a product, they are trying to tell you it's an exothermic reaction. I like to think of it as you get heat out, like I can feel the heat. So if I burn methane, or if I burn methanol, or I burn a piece of wood, I'm going to feel that heat. I'm the surroundings, so I feel the heat. Oh, and by the way, what do you think is going to happen to our thermometer in a system where the system releases energy to the surroundings? What do you think is going to happen? I mean, hopefully you're going to say if it went down in exo or endo, it's going to go up in exo because the thermometer is in the surroundings and the surroundings is gaining energy. I want you to look at this paragraph of text here. This is kind of confusing, so let's read through it together. In this reaction, the system's energy content decreases. It's releasing energy as heat. The potential energy of the products, let's think about that. Any energy being held here is less than the initial potential energy. So these burned and created energy because they had the potential to do so. When you guys look at a piece of wood, or when you guys look at, when you're thinking about starting up a fire pit with your friends, you look at the wood and there's a reason that you need it. It has the potential to burn. So when you burn anything, it's going to release that potential energy as heat. These products will have a lower potential energy. And if you look at the curve, this is the potential energy. Sorry, this isn't very clear because it's so little, but this is the potential energy on your sheet. And you can see that the system lost energy. And here we have higher potential at the beginning than we had at the end. It is generally said that product bonds are stronger bonds for this process because they're more stable. They're at a lower energy and they're stronger bonds. Let's flip this around. How can you guys tell that this guy's endo? Look at where the heat is. Look at where the heat is. So let's underline here. Here's the heat. What do you think that means? Instead of reactants, arrow, products, heat, it's reactants, heat, arrow, products. So the heat is listed as a reactant. The products have a higher potential energy. The products have higher potential energy. Look at here are the N2 and O2, the reactants. And they're going up in energy to the products. So here we have weaker, more unstabilized, or more weaker bonds. They're destabilized a little bit by gaining that energy, and they're at a higher energy. And how did they do that? How did they get that energy? They gathered it from the surroundings. Things I expect you to know very well are the definition of system and surroundings, endothermic, exothermic, how to tell the difference by looking at the reaction. For example, exothermic, heat is a product. Endothermic, it's a reactant. If the Q is positive, it's endothermic. If the Q is negative, it's exothermic. So all of these clues we need you to have. The other major clue you need for tomorrow is, as I mentioned, Q system equals negative Q surroundings. You're going to need to use that in a lot of problems where you guys say, I don't think I was given, again, enough information, but you were. Okay? So I'm going to call this a night. You guys should have 2 pages of notes done. We're going to start on page 3 tomorrow when you come to class. Please read chapter 6, at least maybe the first 2 to 3 sections, so that you guys can have a productive discussion tomorrow and be ahead of the game. And have a good night, and don't forget, I might add a little worksheet, not sure yet, or I'll put the homework set 1 up so you guys can start working on that too. All right, bye.